Okay.
Whenever you like to start, go ahead.
Okay.
Yeah, go ahead. Thanks.
Okay, thanks. So we take it from where we stopped yesterday. The class, the lecture today is shorter, with the idea that we will have more time to go through notebooks. So today I will introduce for you convolutional neural networks for computer vision, and then we will do an exercise with it on the very same problem we had yesterday. So convolutional layers are a kind of architecture that is very central to computing vision these days, in the sense that it's the individual piece of novelty that at some point managed computing vision to jump from 10-ish% accuracy to 90-something% accuracy. So the way this works is that, as we discussed yesterday, deep learning is particularly good in reading directly raw information, as opposed of starting from high-level features that could be justified by some knowledge that you have of the problem. And this is basically the essence of convolutional network. The idea is that you have a network which is structured in two parts. We will see this more in details in the next. The one that processes the image and produce the high-level features, if you want, and then a second part of the network, which is more similar to the things we saw yesterday, that would process these features and will answer the question you're asking. Now, to process an image in raw data, first you need to digitalize it. And this is pretty easy these days because typically you have them already in electronic format. This electronic format means that you have some matrix of pixels, and for each pixel you have an RGB code that tells you the composition of the colors for that pixel. So you can represent a two-dimensional image as a three-dimensional tensor filled with numbers which are between 0 and 1, which is the amount of that kind of color. And doing so, typically we talk about the last dimension, which is the RGB dimension, let's say, as a channel. So when we say we're using a two-dimensional convolutional layer, we are implicitly assuming that there is a three-dimensional input coming in where the third axis is the channel. Let's say you want to process a black and white image, you would not do this. And then you would have the third dimension, the channel would just have one entry. Okay, and this is exactly the kind of problem we will deal with in the hands-on part. So how does a convolutional filter work? So there is a loose inspiration from biology. I would not take this too seriously, but somehow there is some inspiration in that, in the fact that the way we see, I mean, different parts of the images of our retina are sent to the brain, and then it's the brain that puts them back together. So from a point of view of a biology inspiration, if you want, what a convolutional filter does, it scans the image, and by scanning the image, only processes little parts of this, and then things is put back together. But the essence is really in the fact that the reason why this works so well is the fact that it's translation invariant, which means that unlike a normal dense network like those that we saw yesterday, this one keeps track of which pixel is next to which pixel. And the way it works is slightly modified if you move a little bit. If you, for instance, if you decenter the image. Now how it works. So you have an n times n image, which is the big matrix that I pictured there. And then you scan this image with a k times k prime kernel. K and k prime can be the same. In the example, they are equal both to 3. So you have a 3 by 3 kernel. And this kernel has weights, which are the things that you see on the right. The 4, -1, 4, -2, 2, -5. These are the weights of the kernel. So if you have a k times k prime kernel, you have k times k prime parameters. These are the parameters of the network that you need to. When your kernel scans the image, you perform the kind of operation that is depicted on the bottom of the red box. So what's happening is that you do a point-to-point multiplication. So the first element of the 3x3 window that you're scanning gets multiplied by the corresponding element in the kernel, and then you sum them up. And then you move, and you keep doing this for the full image. So the idea is that these things will move to the right, then when it's done, it goes to the bottom, and so on. Doing so, you are filling another matrix, which is the matrix that you see in the bottom. So that's a little bit how the thing works. Another ingredient is the pooling. Pooling is effectively, it's a dimensionality reduction network layer. So what you do, again, you have a kernel as before, and you have a mathematical operation to do the reduction. For instance, you could say, I take a 3x3 window, as in the example there, and I only give back in output the maximum of the values that I read in that window. But you could do the average of them. So we talk about max pooling or average pooling. This is basically a smoothing algorithm. It allows you to remove sharp edges and so on. And the advantage of this is that it reduces the dimensionality of the input, so that effectively when you go deeper and deeper in your network, the dimensionality of the image that you're treating gets smaller and smaller, and so the number of parameters doesn't explode. So then there is another thing, is that while you're scanning the image with your kernel, at some point you get to the boundary. So you need to specify a policy that tells the sliding kernel what to do. So there are several options. For instance, sometimes people say it's called the same padding. Basically, you replicate the last entry. So it's the thing that you see in the top. Like, I'm arriving from the left, the kernel gets to the right, it exceeds the size of the image, and then the last column is replicated to fill the 3x3 window. Or there is, people do zero padding, which is just you put zeros there. And which one to use, of course, is strongly connected to which kind of pooling you're doing. So if you're doing a max pooling, it would be the two padding would be the same, would give the same result. But if you're doing an average pooling, you would get different results. There's another thing which is often done, which is to say, it's called a valid padding, which means that you basically prevent the kernel to get out of your boundary. So here I show you how the things work in practice. So this is with a zero padded image, as you can see, and then you have the kernel scanning. And the kernels, in this case, you see that it shifts by 2 columns, because you can instruct the kernel to do so. And you have 3 images because you have the RGB, so you have the 3 different channels. And each channel gets its own set of filters and produces an output. This we saw yesterday. Batch normalization is important, as we said yesterday, and it's mostly used, it's very much used in convolutional networks for the things that we said yesterday, but you could use it for other stuff. And then, of course, there is the same slide of yesterday to remind you that out of a convolutional operation, you will end up with some 2-dimensional array or 3-dimensional array. At some point, you might decide that you just want to flatten it and you inject it into a 1-dimensional array into into a dense neural network. And in this case, you would use the flattening operation, which is done, you can see in the bottom there. But in general, tensor operations like changing, reshaping, flattening, all these things are available in the library, and it's just a matter of getting experience with it. So this is, for instance, what a convolutional network would look like. So you start with an image, and then you So one thing that I forgot, when you say I have a convolutional layer, this means that you have a set of kernels. So the kernel plays the same role as yesterday the neuron in the dense layer. So when I have a convolutional layer, I can have many kernels the same way yesterday we had many nodes into one layer. So for instance, in this example, the first layer is a convolutional, which has 3 by 3 kernel, and has 64 of them. The second layer has 3 by 3 again, so there's 128 of them. And then after each one, you see that there is a max pooling, and because of the max pooling, the image is getting smaller and smaller and smaller. On the other hand, because you have many kernels, you are expanding in the third dimension. You start with 3 channels, but then you have 64 kernels operating on that, so you get 64. The index in the third dimension is up to 64, then 128, and so on. And see, what you're doing is that you're shrinking in X and Y, but you're making it deeper and deeper in Z, until the very end, where what's obtained is basically a one-dimensional array that then is passed to dense layers. This is a very typical architecture. Now, what do these things do? They work incredibly well. Effectively, when you specify a set of filter, and then each filter has, like you say, 64 filters for one convolutional layer. Each filter has its own parameters, and then when you train, you might learn, each filter might learn different things. For instance, depending on the kind of there is an image, there is an example in the top that you see there, where operating on the image that you see in the picture with the different 3 by 3 kernels, you obtain different kind of effects. And you see effect on the right on the image that gives you the idea of what's happening. And so you see a different allocations of 3 by 3 parameters in the filter can produce, can allow you to detect edges, to blur the image or make it sharper. So these are things that, of course, you could decide by hand that the kind of filter you want to apply is because you want to make the effect sharper, which is the typical thing that you do when you process an image by hand. But in this case, the idea is that you will learn this during the training process. And then people sometimes go back and check what these filters do, and these are typical example of what people call deep dreams, where you get these very poetic and fancy images out of plain image that tells you that somehow the network is doing operations on the image that you would consider extremely untrivial, that you not necessarily they mean something to you, but then they are functional to solve the task. So as for the layer of yesterday, at some point the nonlinearity comes in the game when you put the activation function, and this is why the batch normalization is important. For instance, if you use a relu, you would take an image, you would process it, you obtain the thing that you see on the left, where you have positive and negative values, and then you remove all the negative values with relu, and then you highlight certain features of the image and you suppress others. So again, this is the nonlinearity of the activation function is doing this. And then, of course, as we said before, the pooling has the effect of smoothing your image and reducing its dimensionality. And then the kind of smoothing that you apply depends on which kind of algorithm you use. Now, as of yesterday, there is no obvious right and wrong, in the sense that should we use max pooling or average pooling? It's extremely non-trivial. Then there is a rich literature, maybe even too rich literature, that discusses making this choice and another choice. But many times this is extremely heuristic, and there is not real, like, you can derive some rule of thumb, but imagine, for instance, that you take this kind of rule of thumbs extracted from images of landscape and you want to use them for physics data. it's completely untrivial the fact that the rule of thumb stays valid, and actually typically it does not. So in some sense, applying this technology to a different kind of data set, as we do, for instance, in high energy physics, means that many of these rules of thumb these thumb rules needs to be rederived. So, but it is true in general that when you regard the convolutional neural network, you should think about two different tasks. So the last of these two tasks, which is this one, is the thing that we saw yesterday. So the idea that you start from a set of high-level features and you solve a task with the dense neural network. And yesterday, the features were the features that I told you were relevant for the problem, and so I gave the features to you. Here, we take a different approach. We start from the raw data, and we use a set of convolutional layers to engineer these features that then are flattened into a vector that then is passed to the last second step. But the two networks are trained simultaneously, which means that which features are relevant and what you do with the features afterwards is connected in order to minimize the very same loss function. Then I'll give you a little bit of history, and then we go to some specific example, and notably the one that we're going to play with. So yesterday I told you that 2012 was more or less the year when deep learning kicked off. And in 2012, AlexNet came out, which was basically the first big convolutional neural network, 60 million parameters, 650,000 neurons that could actually be trained only using GPUs. There was Dropout, there was ReLU, so it's really the state of the art was established there. But the idea of convolutional network is older than that. It's basically 30 years older. It started with the neocognitron, which is a kind of network that was intended to be translation invariant image processing with neural networks. And it's basically the seed out of which Jan LeCun came out with convolutional layers in 1989. His task at the time was to basically have an algorithm that could automatically recognize zip codes for the postal service. So he had a data set, which is now called the MNIST data set. That is a data set of digits, where at the time, I think it was 32 by 32 pixels of images of handwritten digits. And he came out with a classifier that could understand which kind of number it was. And the obvious application of this was to automatize the processing of mails, which now it's bread and butter kind of application. But in 1989, it was a little bit mind-blowing because the accuracy that you could reach was unprecedented. And then out of this, you had this MNIST data set, which if you look in the web, for like tutorials of deep learning, it's a typical data set that would be used to introduce you to concepts. Then AlexNet came and the complexity of the problem exploded. In terms of the precision on the very early MNIST data set, basically we saturated in the sense that if you look at the data sets, a modern architecture like the one in the bottom, the GoogleNet, can effectively correctly classify almost all the data set except a few examples that if you look at them by eye, you yourself have troubles understanding which kind of numbers they were. So then GoogleNet 2014 built on top of AlexNet, but introduced the conception of Inception models, which people have been using in high energy physics at some point. And it's a little bit of a counterintuitive argument with respect to the things that we discussed yesterday. So I dedicated a slide to it. It's true that you want to go deep because you want to increase complexity, but the concept of Inception module was to go also wide while you go deep. And so what you do is that rather than having one set of convolutional layer with a given kernel size, you will have a set of them with different kernel size acting on the very same input. And then the outputs would be put back together. You would basically concatenate the outcomes. And And this is counterintuitive in the sense that this parallel processing seems to contradict the idea that you want to go deep in order to increase the architecture complexity. But empirically, it was found that it was boosting performance with respect to the AlexNet or plain AlexNet. And now, to give you the sense of what people are doing these days, these are the kind of networks that you would typically run for computing vision. VJGNet had introduced the use of very small kernels, 3 by 3, even 1 by 1, which before were not considered optimal. And then ResNet was the one introduced skip connection, which is the thing that you see in the top right. So the fact that you take some input, you process it with your layers, and then the outcome of this processing is added back to the input. So you're not learning f of x, but you're learning f of x plus x. And this is again something that boosted performance. And out of this paradigm, people then started to get extremely creative. For instance, the kind of networks that would run in a CCD camera to identify objects, like the kind of things you would do if you're doing computing vision for automotive cars, is called semantic segmentation. The fact that you basically would like to understand, given an image, which pixels belong to a given object. So you would like to cluster. So this is not a supervised algorithm, this is an unsupervised algorithm. We like to cluster the images that you see there of the bicycle all together and the guy on top of the bicycle all together to identify the human, the bike, and so on. And this, of course, when you're thinking about a self-driving car, it's essential to identify the other cars, the pedestrians, the bikes, and so on. And this kind of task is very well solved by this called UNet. It's called like that because it has this U shape that you see. It is effectively a set of convolution and deconvolution network. Deconvolution is basically it's the inverse operation, which you're blowing up and not compressing the information, but the mathematical operation is very similar. Technically, it's a transpose convolution that you're doing. And then with these skip connections. And this is one of the best semantic segmentation networks that is now on the market. And one of the latest image processing networks for classification task is DenseNet 2016 that use the skip connections basically with every other layer. So you see the color lines in the bottom that shows you that this concept of skip connection is expanded to the next level. And now you're not just skipping one set of layers, but you're doing this across the full network. You do understand that where is all of this going? It's a little bit of a random walk into possible ways. People come out with ideas, not necessarily motivated by some theoretical idea. And I mean, this is not theoretical physics, computer science. But, and then they just do experiments, try to understand if their idea works or not. Someone is motivated by some very consolidated intuition of what the networks are doing, but this is not always the case. But certainly the one big issue is that if you look at, yes.
Before going on, we have a question. So let me see if I unmute the.
Yes, the question is just why do this skip connection improve performances? But I think he was just answering this question.
I mean, you can imagine that it depends on what you're doing. For instance, skip connections, if you're doing something like you're trying to learn perturbation around some value, like imagine a regression task. You want to measure the energy of a particle, right? I give you, or for instance, there are tasks in which like you're trying to transform an image. Typical example in energy physics is I give you a generator level object, like a generator level jet, and you want to learn the detector response. So you want to develop a fast simulation algorithm with a neural network. So I give you an X, and I wanted to give you to give me back the x prime, which is slightly perturbed around x by some detector resolution effect. Now, it's easier to learn the delta. And so a skip connection there is a very convenient way in which, okay, I want x hat, x prime, I said, but it's easier for me to learn the difference between x prime and x, and then I add x back. And things like this, this is simply because neural networks are very good in handling small numbers. And if you want to learn 3000 TeV, it's complicated. But if you want to learn the 2% correction to 3000 TeV, it's easier. Now, things like this in an image processing algorithm can happen very often. The fact that sometimes you want to learn a perturbation, and you are better at learning little perturbation as opposed to learning the absolute value. And the skip connection allows you basically to focus on the perturbation and then to add back the input. This is, at least for the kind of stuff that I've been doing, this is the main reason to use this skip connection. Why they are good at classification, I didn't really put a lot of thought about it in the past, but I would not be surprised if it's something related to what I just said for our kind of data. Are there other questions?
No, for the moment, I don't see any. So you can go on.
So we keep going. So the thing I wanted to point out with this image is that on the y-axis, you have the accuracy of these networks on a given benchmark data set. The benchmark data set in this case, I don't remember what's it called. I think it's the ImageNet data set that was used here, but I'm not sure. So basically, you take one data set, you try a different architecture on that. It's a classification task on images, and then all of them are defined to do that. You start with the AlexNet, and then all the different kind of evolutions that you had, and you get to the ResNet, the BGG, the ones that I were mentioning before, ResNet, DenseNet, Inception, and so on. And what you see is that, of course, at some point you are saturating in accuracy, but you start from 55% and you get to 80% accuracy. But the other thing that you learn, if you look at the y-axis, the x-axis, which is the number of operations you're doing, this is just exploding. And also, the size of the blob tells you how many parameters you're dealing with. So the thing here is that, of course, these networks are extremely well-performing, and they're getting better and better and better, but there is a computational cost behind, which is non-negligible, which is also why people are now looking into ways to optimize the inference phase. So when you run your network, for instance, running on GPU is extremely good if you can analyze batches of images at once, because you can parallelize the inference step. On the other hand, GPUs are extremely consuming in terms of power. This is why people now are looking into FPGAs, like to save energy effectively and have less money spent into the operating computing centers, for instance. But the idea here is that clearly when you are behind this kind of things, people don't put themselves into the thing of, let's try to find a solution for a constrained problem. And this is not necessarily good for high energy physics, because imagine that you want to do this in a trigger of an experiment, then you have very limited computational resources. And the memory of the job that is running in a high-level trigger, for instance, a couple of gigabytes, and you can just make it blow with neural networks because you have to do everything else also. So the thing is that effectively, it's also true that our data are very different than this. So if you would put I had the slide, not this one, where I have like a point that was representing a network of our kind of network into this axis, you would basically be sitting across almost on the y-axis, very, very high in accuracy with a very small point, in the sense that the kind of things that we do require less computational power than this kind of tasks. So understanding an image is much more complicated because typically you don't have a theory behind it. Now, to give you an idea of what people have been doing in energy physics with convolutional networks, I put out two examples. One is the very first one. This was the first paper that came out using convolutional networks for high energy physics, and it's for neutrino detector. They were trying to identify electron muon neutrinos using convolutional layers. And for them, of course, this is a very ideal thing to do because the detector effectively is a three-dimensional tensor. It's an array of three-dimensional sensors that it's a three-dimensional array of sensors which record energy. And so the data, the raw data is a tensor itself that you can just process with convolutional networks. This is not true at DLHC, for instance, where the detectors are cylindrical, they are made of different parts, these different parts partially overlap, geometry is more chaotic there. But for neutrino, it's very, very easy. And what they showed is that for the easy ones, which were, if I'm not mistaken, the muons, I don't remember. So they tried muons and electrons. For one of the two, they recovered state-of-the-art performance. It was for the easy one. I don't remember. I would say the easy one was the muon. But for the other one, they had that there is a raised end. Yes. But I keep going in meanwhile. So for the other one, there was like a jump in performance. That would,
No, a moment,
yes.
I had to give the rights to
right. Okay.
Sorry, thank you. I don't quite understand, like for the nova neutrino task, why would a convolutional neural network be a better choice than like a deep neural network? Because wouldn't they have non-image data that they could use? Wouldn't it be computationally more expensive to use a CNN rather than a DNN?
It is computationally more expensive. CNNs are more expensive than DNNs in general because they have more operations to do. And if you think about a DNN, so there is something I didn't touch yet. I was about to get there, and it's something that you see if you look at what their typical image will look like. I like a natural, the kind of image you can take with your smartphone, where every pixel counts, every pixel is bringing some information. A typical high energy physics event is basically a set of zeros. It's pretty empty. And then you have here and there something which is not zero. So the image is extremely sparse. And if you read the convolutional network literature, basically it's full of caveats that say, if you have something sparse, don't do this. On the other hand, it works. People try it. So it's true that computationally, it's not necessarily the most effective thing to do because the majority of your computation will happen doing, you move your kernel, your three-dimensional kernel, and then what you end up doing is a bunch of something times zero because just there is no energy deposit there. On the other hand, there was a clear gain in performance, and this is because most likely convolutional networks are better than what people think they are with sparse data. It's not the only thing you can do, of course. There are other kind of architecture that you could use. So the big advantage of convolutional network with respect to the dense would not be the thing I would do. So I could say no. I could take their image. I could try to compute some physics related motivated quantity and use the DNN on that. But in this very specific problem, I don't think that you would succeed very much because there is not really, it's not like in a jet, I say, okay, I have a jet, I can compute the jet mass, the jet multiplicity. There are not so many physics handles you can use in order to digest an image like that. This is a pattern recognition problem. On the other hand, the convolutional network, on the other hand, though, the convolutional network has the advantage that it's translation invariant. So, for instance, the network doesn't care where the thing is happening. While then, if you consider, for instance, to just inject in the network those few hits which are not zero, you would have problems of how do you order these hits, and what happens if you take this very same event and you translate it 3 layers down. You will have a completely different processing, while the convolutional network will give you the same answer. So this is to say that there are clearly advantages. Now, it's not the only thing you can do. And if we manage to get there, in 2 days, I will show you a graph neural network, which is what I would have done here. Not sure if you can get better results, but for instance, for high energy physics, for LHC data, it seems to be working better. And in that case, what you do is that you abstract completely away from the geometry. You represent each of these dots as a set of numbers, which are like the coordinates and whatever else you think is relevant, how much energy was recorded and whatever you want. And then you process these sets of dots, regardless of the underlying geometry. We will see that. But in any case, this was to show you what was done. And this to me works very well when your detector is very regular. When your detector is irregular, you run in troubles. And unfortunately, the majority of the detectors we have now are very regular because they were not designed having in mind machine learning. But these guys happen to have the right detector in range. There is an exception for collider physics, which is the next generation calorimeter, like the calorimeters people were considering for the ILC, for click, for this kind of E plus and minus colliders. Effectively, they were very similar things. They were three-dimensional arrays of sensors. So you could do this. We tried, and for instance, to do electron versus pion classification or photon versus pi zero classification. And here you have a comparison with BDTs or DNNs, where effectively what we did were we just take the inputs and, as I said, and we just flattening into a one-dimensional array. So BDTs and DNNs, you see, for instance, comparing DNNs to BDTs, you see why deep learning is better than other machine learning. But then if you look at the CNN that we trained, it's even better. And what is called GN there is GoogleNet. So this gigantic thing, what is it? This thing that you see on the bottom right. We use GoogleNet and it gets even better. Now, of course, it's a little bit counterintuitive for a physicist to imagine that you put so many degrees of freedom to optimize, and at the end of the day, the majority of them are completely irrelevant. So it's computation, from the point of view of the computational efficiency, the outcome of your network, of your training would be extremely inefficient. And then you will have to work on it to make it more efficient. And there are techniques to do that, but we're not gonna discuss that because as we said, the inference aspect go beyond the scope of these lectures. So now we go back to our problem. So yesterday we saw that we wanted to classify these jets. And the way we did that is that I gave you a list of 16 features that were meaningful to do this task. And then we trained together a dense neural network that was doing the decay. Now let's try to take instead a different paradigm, and let's try to solve the very same problem with convolutional layers. So what you would do is that you go back to the list of constituents inside the jet. So all the particles that you have in the jet. And then you would consider this basically the angular, the solid angle of your jet, of your cone, let's say for simplicity, and you would pixelate the solid angle. So in this case, it's eta and phi. So phi is the azimuthal angle, and eta is the pseudo rapidity. So it's not exactly an angle, but sort of. So once you pixelate in eta and phi, you have these pixels, and in each pixel, you do the scalar sum of some energy related quantity for the particles that end up being there. In the dataset example that we give you, it's the scalar sum of the PT of the particles that fall in the pixel. And so a jet would look like an image of the kind that you see there, that you can process with a convolutional neural network. Now, this is the very first thing that people have been doing with convolution, with deep learning in high energy physics. You have to understand that you're not, it has some pros, which are the same that we discussed before. Particularly, it is very handy to do this. On the other hand, this fact that you're pixelating your data set means your jet means that somehow the pixel size becomes a limiting factor, in the sense, okay, you could say I take the resolution of my detector as the pixel size. The problem is that the resolution of your detector is not a number. So you will end up picking something, and that might be, typically it's way bigger than the resolution of your detector, so you're losing information. So somehow you're getting a problem, and you are hammering your problem inside an image, your data inside an image, in order to fit the architecture you want to use. While in normal life, you should be the other way around. You start from your problem and you should engineer an architecture that fits your problem. We will see that in 2 days. But for now, let's take this as the standard. And so this is now, it's yet another image, except that you have only one channel, which is the energy, the PT. And this is the kind of things that you produce. This is not a single jet. This is the average image. So it means that you sum all the images in the data sets and then you divide it by the number of jets. And you see that, for instance, for QCD jets, which are on the left column, you have something which is centered on 0 at the origin and very symmetric. While in the other case, which are W's, I think, you get these two blobs which are overlapping. And so you see that the image is different. And this is the kind of behavior that you would like your network to understand. And this is what we're going to try to do. So this was it in terms of what convolutional networks are, where do they come from, and what they're good at. I tried to keep it short so that we have time to play with the data. But if you have questions, I think we can spend a few minutes answering them, and then we keep going to the hands-on part.
So thanks, Maurizio. If there are questions, please raise your hand and I will allow you to unmute your microphone.
Doesn't seem so. So
I don't see anything.
yeah, so we go to the
Maurizio, may I ask you a small curiosity?
Sure. Yes, go ahead.
So you showed in this jet reconstruction that you use the 2D image recognition.
Mm-hmm.
But is it possible to do also with something analogous to convolutional networks in 3 dimensions?
Sure. So
if you have tracks and other stuff.
Exactly. So you could do, basically you could do images for different kinds of particles. This is actually what people normally do. Mm-hmm. So you would say all the neutral, all the neutral hadrons, the charged hadrons, and you put them on different layers and use that as a channel. Certainly. Other things you could do is that you could do something which is more detector specific, like you could say these are the electromagnetic calorimeter cells, these are the hadronic calorimeter cells, these are the tracker cells. But this is where you start going trouble, because if you want to put already this, if you want to put it into, this would be extremely more like raw data specific, because you don't, in the other case, you first reconstruct the particles and then you separate the particles with particle flow, and then you separate the particles by the particle kind. And then you try to go back to something which is related to the detector resolution. In the other case, you really try to enforce the geometry of the detector. The problem is that the geometry of the detector is not trivially encapsulated into a regular size tensor. So already you start to go in trouble. Then the other problem is that the dimensionality of the image at the level of HCAL, ECAL, and the tracker is going to be different. So at the end, when you try to do something more sophisticated, you really start to hit the limitation of your approach. And of course, you can take shortcuts, you can take approximations and do simple things which are reasonable and get very good results. My take of this, though, is that, again, what I think we're trying to do is that we're taking a hammer and we're trying to hammer down our data into a regular tensor, which is not what our data are. Our data are sparse sets of sensors coming from very regular geometry. So to me, the best approach instead is that you forget about the geometry of your detector, you try to abstract away from it. And for that, I would have used instead graph networks. We'll discuss this. So basically, in the graph networks, we still have the memory of the geometry of the detector because each point, each vertex of the graph, each particle, you would represent it also with its coordinates. And so you still remember where things are, but in a less graphic way, let's say. Okay.
Okay, thanks. So I still don't see any questions, so I guess we can go on.
Yeah, so as of yesterday, as we did yesterday, we'll start from Colab. So the question I have is, do you want to look at me doing this, or I think that something more interactive would be more interesting. So what I would like to understand is how many of you are trying to do what I do things. In some sense, I can show you the thing, or we do it more like a tutorial where we pause and I give you the time to try things. So for instance, you could raise your hand if you would like to do it more interactively and as a tutorial thing where we pause and we take time. See, people are raising hands. Yeah. So let's do it like that. In which case, okay, we might have some problem. Everyone unraise the hand. So what we're gonna do is that we go step by step then. And I don't know how we can handle this with the mic. But if you have troubles, I think the best is that you write it in the chat. So I open the chat in front of me. And so I look at that.
The chat in principle is open for everybody, so all
Okay.
participants can write down something there.
So again, collab.research.google.com, you log in, and then you write Pierini tutorials. So the first thing that I would like to do is, before going into the convolutional 2D, which is this notebook 3, I would like to go back to the notebook 1, because yesterday I had some questions about it. So the fact that there were questions means that this was not clear, and I think it would be nice to spend some time on this. So here I'm just downloading the data sets as usual. I would like to show you the structure of the data in the files that I give you. Let's say for the next 10-ish minutes we do this. And then we move to the CNN itself. So the data, as I said, are these jets, but the jets are in the data set are stored in different formats. So yesterday we saw the list of features, let's say, and today we're playing with the jet images. So you see that you have different kinds of jets of data sets. So yesterday we played with this. So the data set which is called jets as the features, and there is something which is called jet features names, which is this array of strings tells you which quantity is which, okay? In particular, if you look at the very end, these 5 here, these are the Boolean that we need in order to set the target. So these are Booleans which are set to 0 or 1, and it's 1 when that given jet belongs to that category. So this is the gluons, the quarks, the W, the Z at the top. So our target looks like this then for gluons, looks like this for quarks. Do you see my mouse?
Yes, yes, we see it.
Okay.
Mhm.
Okay. And then you have the W's, the Z, and the top. So when we want to, so what we're gonna do, we're gonna train a network that has 5 numbers in output that should approximate this for gluons, this for quarks, and so on and so forth. So what the first thing we have to do then is, yes.
Would you try to enlarge the window because
Sure, sure. Yes. Is it better?
yes, now it's much better. Thanks.
Okay, so the point is, this is what I meant yesterday by one-hot encoding. We could have taken a different kind of approach. We could say, okay, let's call gluon 0, quarks 1, W's 2, Z 3, and top 4. People sometimes do this, but this is a much better way of doing it because it looks like stupid, but for a network, learning something between 0 and 4 is not the same thing as learning zeros and ones. And particularly if you want something which is probabilistic in output, this is way, way more convenient. Okay, so this is what people typically do. Now, the first thing we have to do when we play with our data is, so here I am opening, I have the file open, upstairs, above, I've done it. I open the file here, okay? This is an HDF5 file. I open the file there, and I read the file as an NumPy array. And then I'm selecting columns -6 to -1 excluded. So I'm selecting these columns here. And I'm taking all the rows. This is my target data set. Okay. And if you look at it, it's what we said. These are like the first 5 entries. The first 2 are gluons, then there is a top, then there is another gluon, then there is a W, and these are the last 5. Okay, so this piece of code will be in all the data sets that in all the notebooks that we have, because this defines our target. Okay, then in the file, there are other data sets. So there is the jet image, which is the thing that I just explained you. So it's going to be a bind. It's done here. Let's look at it. So these are the features of yesterday. I'm not going to rerun it because all the plots are already there. These are the features. What's going on? These are the features of the jets that we handled yesterday for the different categories. So for instance, you see the jet mass is clearly a discriminating quantity for the different kind of jets. This is what is called jet substructure, tau 1, tau 2, tau 3. These are physics motivated quantities that we used yesterday. There are more than 16. I reduced the exercise to 16 because this is what we have done in this paper. But now the image data set. So here, again, I have my categories. So I'm reading out of the same file, I'm reading the jet image data set, okay? And then I use the target. This is called in NumPy, it's called a mapping. I'm using the target, looking at, I'm basically selecting, I'm selecting the events, I'm selecting the subset of images such that the argmax is equal to 0, 1, 2, 3, 4, and 5. So I'm selecting separately the gluon, the quark, the W, the Z, and the top just to make plots. And these are the kind of plots that I get. This is the average image again. So I sum across all the images, and then I show you the sum of the image. Okay. Now you don't see the things that I showed you in the image because unlike the data sets in the image that I showed you in the lecture, these are not rotated. Those were rotated such that if the image was elliptical, the ellipses would be vertical. The long direction of the long axis of the ellipse would have been vertical. Here, we don't do that. Since the problem is symmetric for rotations around the axis of the jet, you end up seeing all symmetric things. But you do see something which reminds you of the physics, the fact that the showering is wider for the overlapping jets. See, the top is even more clear. So these are the kind of images we're gonna play with. And no, I didn't have printouts. We'll have the printouts. This is for tomorrow. We're gonna maybe look at this tomorrow, but tomorrow we will play with lists. So we will take a list of particles, and each particle will be represented by its momentum. And see that you have px, py, pz, the energy, the relative energy. So energy of the particle divided by energy of the jet, and so on and so forth. And these are features that are per particle. And then each jet, so you have 10,000 jets, for instance, each jet has 100 particles inside, and each particle has these 16 features. And then we're gonna play with this list. And we will use other things than image processing. So, but today we concentrate on images, okay? Now, so let's do this together. So everyone should open the notebook. So again, you do Pierini tutorials. And you pick the notebook 3. And again, if you have troubles, just raise your hand and ask questions. So, no, sorry, I forgot. First thing first, today this is important because otherwise it takes forever. Change the runtime to GPU. Okay. So now that Google kindly provided you with a GPU, you run the first cells. This is the usual stuff that you download the data set, and then here you append the data out of the 5 files. And as I told you, we play with the jet image, and that's your target. And we play with the last, next to last 5 columns to build the target. And then you concatenate these data sets across the 6 files in order to create your final data set. This is what this code does. Okay. So as of yesterday, we have 50,000 jets. We have 5 targets, the 0, 1. And our images, you see, are 50,000 jets. Each jet is an image of 100 times 100. Okay. Now, as of yesterday, we split this in train and validation using this function train test split of scikit-learn. And we do this, the splitting proportion is 2/3, 1/3. So the test data set is 1/3. The validation data set is 1/3. And this is what we come out with. This function does things for you. It randomizes the images. So the order is shuffled, but it's shuffled coherently for the X and the Y such that you don't keep the correspondence. Now, as I told you, our image is 100 by 100. We miss the 3rd dimension, which is the channel, because the convolutional neural network expects the 3rd dimensions to be there. So what we do is that we're going to reshape the tensor to X shape, Y shape, Z shape. So this is number of jets, number of pixels in X, number of pixels in Y, and the channel 1. And I do this both for the training and the validation. And now my data sets have this extra index, as you can see here. While of course the target is the same because we didn't touch it. Okay. This is everything we had to do for the data preprocessing. Now, this is the model itself. Now I have again a bunch of includes. I still use dropout. I put the extra index. The extra index is the channel. So it's like RGB for a colorful image. We don't have color here because we only have PT in the pixel. So we have one channel if you want. But the point is that you have to physically create this extra dimension. Otherwise, the convolutional the library, the Keras, runs in trouble because it expects it. So a two-dimensional convolution would expect two-dimensional images with an extra dimension with this channel. A one-dimensional convolution would expect one-dimensional input and then a second extra dimension, which is the channel. So the size of the tensor is always +1, okay? Of course, +2 if you include the fact that you have a bunch of them, not just a single image. Now, these are my usual, I'm not even sure that I'm using all of these things. Then most likely yes. So, okay, this is just I define for convenience, then dimensionality in X and Y, these are 100 and 100. And so my image is 100 times 100 times 1. I could have written this hard-coded, like I could have sent this. It was, it's the same. And then I have a dropout rate of 0.25. So here I get the model. I start, I have my image shape. So I defined an input layer with this exact shape. This is the syntax. And here I allocate my first convolutional layer, which is a conv2d with only 5 kernels. The kernel size is 5 by 5. Data format channels last, I think, is the default, so it's not needed. This is to say, to tell Keras, look, the channel is the last of the 3 dimensions. Not, you could also do channels first, so you could put the channel here, but I usually put it at the end. And you tell Keras, look, the channel is the last one. I think that this is default, so it's not even needed. Strides is how much you shift the kernel when you move. In this case, I want to shift by 1, which means I want to basically progressively move right and top bottom. The first index is left right, the second index is top bottom. If, for instance, I have done like this, 5, 5, I would be using kernel that jumps to completely independent patches of the image, which typically gives worse results. Then padding, I'm doing same, but I could do valid, I could do 0, as we said. Okay, so this is the convolutional kernel. And this does exactly things we discussed. Once I've done this, I batch normalize the output and I inject it to the activation function. This is a syntax that is new, it's different than what we had yesterday. I updated the notebook of yesterday such that the very same syntax is used in one of the dense layers so that you can see the difference. In one case, you can even do it here. So you would say here, activation equal rel. But if you do this, you cannot put the batch normalization in the middle. So what you do is that you don't put an activation function here. You put the batch normalization, and then you do apply the rel as if it was a layer. Okay, it's an activation layer. Then I do a max pooling, but I could do average pooling. If you do average pooling, you need to include it here. So you will have average pooling to D and so on. And then after again, you have a kernel size, which is called pool size in this case, 3 by 3, 5 by 5, we were here. And then again, I put a dropout just for regularization. So this block, so convolution, batch, activation, pooling, dropout, I repeat it twice with different parameters, okay? Then the output, I make it a one-dimensional array and I pass it to to a one-dimensional, let's say 10 here, to a one-dimensional layer with 10 neurons and ReLU activation. And then the output is 5 layers with softmax activation like yesterday. The first argument of the conv2D is how many kernels you want to run. So here you say how big is the kernel, how it moves, what does it do when it gets the boundary, but how many of them you want to put there. And I put 3 of them. I could put 30 of them. Okay. Now, this model is ridiculously small because it has only 5. Yes, you will see. The question is, does it mean that it's how deep the next layer is? It's basically that, and you will see it if I let me compile it. So the compilation, again, you need to specify the loss function, which is dictated by the kind of problem you want. It's a classification with multi-classes. It's not binary, so we use categorical cross-entropy. We optimize with that. So this is the model, and this is exactly what was just asked. So you see I start with 100, 101, but then I run my conv2D, which has 5. It has 5 kernels. And so I get an output which is 500, 500, 100, 105. Okay. So you see that I'm getting expanded in the third dimension. Then the batch normalization doesn't change the dimensionality of the tensor. And then I run the activation, same thing. Then I run the max pooling. Max pooling has a dimensionality of the pooling layer size is 5 by 5, which means that each 5 by 5 window, I take the maximum of the window, and so, not by chance, the output, the 100 times 100 becomes 20 by 20. But I have 5 of them. And then dropout doesn't do much. So here you see the number of parameters. This is interesting because you see that the first convolutional has 130 parameters. And then there are 20 extra parameters from the batch normalization. These parameters, what are they? It's basically it's the mean and the sigma by which you shift and you rescale the quantities such that they are centered and with RMS one. But notice that these parameters are they're trainable to some extent in the sense that you learn them in the training, but it's basically mathematically determined. It's like you take your batch and you do the mean and the RMS of that batch. So the reason why I'm running, so the question is why I'm running the conv batch normalization twice. It's the same as why I'm using 2 hidden layers. So you can look at this as this structure as one hidden layer, and I'm just stacking 2 of them because I want the network to be deeper. And the reason why I want the network to be deeper is because typically it would give me more complexity and it should give me better results. But one exercise you can do is just you take one of the 2 and see what happens. Okay. You could even put more of them. And here, unlike yesterday, you have many more degrees of freedom because you could change the stride. You can change the padding, even if typically it doesn't make such much difference. You can change the kernel size. You can change the number of kernels. You can change the activation function, the kind of pooling you use. So you see the number and also the size of the pooling. So the numbers of degrees of freedom now explodes. And this means that the landscape of possible networks you can come out with, it's much, much different, okay? Another thing that I want you to notice is the number of parameters, because, so this is the first block, and then you have the second block of conv2D, and you see that the output of the second block is a tensor which is 6 times 6 times 3. And now what I do is that I flatten this into 108 numbers. So I turn this three-dimensional tensor into a one-dimensional vector. And then I pass it to a dense layer and then to the output. Notice that the total network, in total, the network has 1,500 parameters, but 2/3 of them come only from the dense layers. And this gives you the idea of what's the difference between convolutional and dense is also in the number of parameters. Convolutional networks has a lot of operations, but has less parameters because the parameters are the quantities that enter the filter, and then these same quantities scan the full image. So when you define a 3x3 kernel, you're allocating 9 parameters, but these 9 parameters process the full image. While with dense neural networks, this is like this tend to explode, like the combinatorial tend to explode much faster. And so out of the parameter, the majority of your parameters are in the dense network, okay? This model is pretty small, okay? It's also true that we only have 50,000 events, so. Then I'm training it for 200 epochs. And as we did yesterday, I'm putting early stopping. So if I see that it doesn't get better after 10 epochs, I just stop. But also I apply some reduction of the learning rate if I see that it tends to plateau. Now, for your amusement, you could try to do the very same thing, specifying here in the runtime known, which means you don't allocate a GPU and you just go on a CPU, and you would see that it gets way, way, way slower. And since for industrial purposes, basically, if you think about the industrial applications of deep learning these days, half of them is image processing, the other half is natural language processing, which is the kind of stuff we're gonna see, the kind of network we're gonna see tomorrow. You understand that if you can speed up convolutional neural networks with GPUs, this is why it's quite crucial. And this is why a lot of the technical developments have been going in this direction. So now this training, it would be nice if you run this, but you try to change something there. So you will see that at the end that the kind of accuracy that we'll get out of this model is comparable to the one of yesterday, even if this model is pretty small. But if you start to go with large number of filters, and maybe you try to make this smaller, the number of parameters gets bigger, but typically the network should get also better. So it would be nice if you try to train something else than this model, then we can compare results. So this will take a few, typically within 50 epochs, it stops. The training is stochastic in the sense that the starting point is randomized. And so if you run it twice, you get different results. Typically similar, but different. If there are questions, that's a good moment for a question. If someone is running in trouble, you can also ask that kind of questions. What would be a systematic way to change the hyperparameter? There is not really rule of thumb. There are rule of thumbs, but they are extremely problem specific. So in this case, it's not like easy to read computer science literature and say, okay. So typically what I do is that I try to decide a priori which are the hyperparameters I want to change. And I run what is called a Bayesian optimization. What I'll do is that, so while this thing, oh no, it stopped. So I'll give you, I'll put this repository on the Slack channel later. This is very similar to the notebooks we're running. This is the code of the original paper that we wrote with this data set. And for instance, this is the hyperparameter scan of the very same model you're playing with. So you had to define some class that has the kind of nuisance parameters of hyperparameters you want to optimize for. For instance, in my case, is how many layers I want to put for the CNN, what's the size of the filter, what's the size of the max pool filter, which are kind of activation function, how many neurons in the DNN, how many DNN layers, what's activation function for the DNN, how many filters. And these numbers were somehow extracted by a Bayesian optimization algorithm. And then for each point, I would do a training. And so what I do is that once I receive a set of parameters, I would call this build function. And the build function does exactly the same thing that you saw before, except that it allocates blocks in loop in 4 cycles, because I don't know how many I'm putting by default. So it's a little bit more tricky to write the model, because you need to write in such a way that the code adapts to these different things. But it's the very same code that you're playing with, if you look at it carefully. And then it's the same fitting. It's a little bit different because the data set is bigger, so there are things you need to do. It's called data generation. So you don't load the full data set at once, as we're doing, but you only load it in chunks, not to saturate the memory. But the Bayesian optimization is effectively happening here. There is some library which is called gpyopt that runs the Bayesian optimization. You specify the model, and then it runs iterations, and you say, give me you make it record the x and the f. F is basically it's the output is that it's trying to minimize the loss function across different models. And then you let it run for a week, and after you get the best model out of it. Okay. Then there was another question: whether are non-trainable parameters, because the way the batch, I think it's the batch normalization that has the non-trainable parameters. It's the way the batch normalization is implemented in Keras, but not just the batch normalization, but in general, there could be parameters which are like deterministic functions of your input. So for instance, if you want to compute the mean of a quantity, you get your batch, you compute the mean. That's a parameter that you can use, for instance, to shift your data. And that's not something, it's a parameter of the network because it's something that changes depending on your data, but it's not a trainable parameter in the sense that your stochastic gradient descent doesn't depend on it. You don't take a derivative with respect to it. And so it's a non-learnable, it's non-trainable in the sense that you don't compute a gradient with respect to it. Now, to know which one it is, we will have to open the batch normalization implementation in Keras and check. I think it was the mean, but I'm not sure. Are non-trainable parameters with the activation function? Yes, sometimes. It depends on the activation function. There are activation functions which are parametric. For instance, people have been playing a lot with this idea of ReLU, but trying to generalize it. ReLU has this, on the negative value, it returns 0. There are things which are called so this thing, so these are the different variations of activation functions which are related to ReLU. So really, Ricky ReLU, you see its difference. It's not, so for positive values, it's the same as ReLU. For negative values, it's a parametric dependence on X. And this coefficient here you can even change it, and this becomes a non-parametric parameter, a non-trainable parameter of the network. It's technically, I think it's an hyperparameter. You can fix it by hand. But as you see in our case, there is no parameter at all in the activation, so it's just fixed thing. So the training ended.
Maurizio, there was a question by Jörg. I'm not sure it can speak. Let's see. Or
So yes, I'm still here. So can you hear me?
Yeah.
Yes.
Okay. So my question was, maybe I missed it, but about the parameters of the convolutional layer. So in the notebook that you showed us, I mean, for the first one, the 5x5 with 5 layers, there's 130 parameters. I was wondering, why is it 130? Because I mean, a quick counting I would have guessed it's like 5 times 5, so 25 for one layer to get the matrix, and then maybe times 5, which would have been 125. So what are
the other 5? Good questions. I think that there is a bias for each. So because the mathematical operation is that you do the point-by-point multiplication. So you have your 5 times 5 window. You have your 5 times 5 kernel, and then you do point-by-point multiplication. And so you have, as you said correctly, you will have 25 of these parameters. Then you sum, and you get a number, okay, for each of the kernel. At that point, you add a constant. That's a bias, like we did in the dance. It's completely irrelevant, though. So the bias is there. There is an option, I forgot, I should have put it here. There is an option to remove the bias. So to say, don't put the bias there, then the number of parameters would have become 125.
Okay.
It is better to do so. Why? To remove the bias, because then we apply the batch normalization. The batch normalization rescales the input and makes the bias completely irrelevant. And so somehow, because I put the biases there, but the bias is playing a role, I have a flat gradient. So the direction, my loss function in the direction of the bias is flat. The gradient is flat. And so the optimization is just picking some random number there. And this is not good. So good point. I don't remember. There is an option in the convolutional layer that allows you to remove the biases. I will have to check which one it is, and then I will correct the notebook.
Okay. Also, for the second convolutional layer, so it says there's 138 parameters. This I don't understand at all, because I mean, now this is small.
I think this has to do with the fact that I think that there is some padding in the middle. Let me think. Because the fact that 3 doesn't divide 20. So what happens? We have, it would be 3 by 3 is 9 times 3 is 27. How do we get? Oh no, and then there are the 5. So wait, it's 3 by 3. It's 3 times 3 times 3, 27, and then it's times 5 because there are 5 dimensions, 5 indices. 27 times 5 is 120 something, and then there should be some bias around. I think you get back there.
Okay, yes. So
the reason why we didn't have this problem here because we only had one channel, right? But if you look at, let me show you.
Yeah, okay, it's because we already have 5 channels at this point.
Exactly, and the filter goes by channel. So you apply different filters to your red, your green, and always think about the image to understand what you're trying to do. For instance, if you want to learn sharp edges, the sharp edges are not gonna be the same for the green and the blue and the red. in your image. And so you would like to have the freedom that the kernel learns things on the blue layer of your image, which are different than the things that it learns on the red. And so you don't constrain a given kernel to have the same values on the three edges, on the three channels. But I have to do the math to understand if with the bias I get there. I always get confused with these things.
I think it makes sense. 5 times 27 plus 3, isn't it? But, so it's 130.
I would say so, that you have to add the three biases at the end, right? So yeah, 135. So that's our training. And as you see, as we expected from yesterday, the validation gets better than the training loss because of the dropouts that I put here and here. I didn't put the dropout after the dance. I could have done it. Actually, most likely it was wise to do that because the majority of the parameters are after the dance. So if you overtrain, most likely you're overtraining here. You're not overtraining here. Sorry, here. But I mean, this is what I had. You can, again, feel free to play. There is no right, there is no wrong. And in terms of accuracy and AUC, it's similar to what we had yesterday. But yesterday, one of you sent a trained model which was way better than this one. He had something like AUC and 90, 93, 94, pretty much the same as I got in the paper with the full data set. So that was very impressive to me. And here is the same story, that changing the parameters and in particular using a bigger network, I would expect you to be able to do more. So what's the target value for the loss? For a binary, it is for a binary classifier, it would be 0.7-ish because it's if you take the expression of the binary cross entropy and you just put the numbers there, this is what you get. For many classes, I'm not sure, because it is sum over category of, it's basically a relative entropy. Don't remember, but it's easy math. So let me open on Wikipedia because it's faster than if I open in the slides. So the expression is this. So px times log of qx. So your ideal target would be that yeah, to tell you that so if the 5 classes means that your target probability is 0.2. So basically you will have 0.2 times log of 0.2 5 times. So the sum is over 5. So it should be 5 times 0.2, which is 1. So it should be log of the logarithm of 0.2 minus logarithm of 0.2. I think we're done, by the way, because Fabio just made me realize that it's already 3 p.m. So this is what it is. As of yesterday, it would be nice if you just write on the deep learning channel what you get. And I think maybe we have time for the last question and then we close because we're running out of time.
Yes, thanks, Maurizio. Please, if there are questions, it's time.